Alright, so I figured since I wasn't going to be here today, I would just record myself. And this is wicked weird because I'm after school right now and there's nobody here, so it's very strange. But it should be beneficial to you, so that's why we're doing it, right? So, homework should be out. Answers to the homework. The front of the worksheet here, you have the answers, right? But I wanted to go through some of them. So these two here are for the dilution problems. So those are the two dilution problems. These two are the parts per million questions on the back. The molarity problems I am not going to go through. Actually, you know what? I will go through number 4 real quick. But I already have these up to save a little bit of time. So let me do this quick. Number 1, the dilution problem. How do you prepare a 250 milliliter solution of 2.35 molar HF dilution from a 15 molar stock solution? So 15 is M1, M2 is 2.35, V2 is 250. That's your desired solution. What you have to do is solve for the volume like we did yesterday with the solution up here, the purple one, potassium permanganate. You have to figure out, okay, how much do I need of the stock solution? So basically what you would do to make number 1 to answer the question completely is you would take 39.2 milliliters, add it to a 250 milliliter volumetric flask, and then fill it to the line with distilled water to get your 250. And yesterday I asked a question that I never answered, or I totally forgot about. I asked you guys, how much water do we need? So when I was doing the stuff up here, I said, how much water do we need? We needed 1.25 milliliters of the stock solution, but how many milliliters of water? You would just take 250 and subtract 1.25. That's how much water you would need. So the same thing here, you would subtract this from 250, that's how much water you need. But again, if you use one of those flasks, which I brought it to the back, the one I used yesterday, you just fill it to the line with distilled water and then tip it upside down a couple times, you're good to go. So that's how we do number 1. Number 3 on the dilution, they give you volume 1, that's the volume of the stock solution. They give you M2, that's the dilution. They give you V2, you're looking for the concentration of the stock solution. So you do the math, 4.64 moles per liter is number 3. Okay, now on the back, I'll come back to the molarity problem. The first parts per million question, I give you the grams of the solute, I give you the grams of the solution, divide, multiply by a million, 3,232 parts per million. So I got those numbers from, I found that problem. That's not realistic, but whatever, it's good practice for the equation. Number 2, this time a little bit harder, right? We're looking for the grams of the solute. They give us the parts per million, they give us the grams of the solution. So what I would do is divide by a million, right? I didn't show the work, but divide by a million, divide the 6 by a million. So then I have one number equals x over 1500. Cross multiply, I get 0.009. I think I just looked at it, it's kind of hard to see those decimal points. So 39.2, 4.64, that's 0.009 grams. So that was how we did, those are the answers for the first 2. Not the first 2, the 2 on the back, that's the answers. Before I forget, the review book due tomorrow, chapter 3, it's over here on the side. And I'm not giving you anything else due Friday, due tomorrow, which is Friday for you guys. Yeah, don't forget that review book, chapter 3, separate paper, please, don't forget. All right, real quick, let me go over number 4 on the front, the molarity. All right, so number 4 is one of those 2-step problems. How many grams of CaCl2 would be required to produce 3.5 molar solution with a volume of 2 liters? So we first use the molarity formula. Molarity equals moles over liters. For molarity, we plug in 3.5. X goes for moles, and 2.0 goes for the liters. Cross multiply, X equals 7, right? So 7 moles, right? 2 times 3.5 is 7 moles of calcium chloride. Now we can figure out how many grams we need, right? Because the question says how many grams, by looking up the gram formula mass of CaCl2 on the periodic table. So Ca is 40, each Cl is 35 plus 35, right? So 70 plus 40 is 110. So 110 grams are in 1 mole according to the periodic table, right? Because that's the mass of calcium chloride, 110 grams in 1 mole, grams per mole. That's the unit on the mass. So that's our first part of the ratio. We want to know how many grams are in 7 moles, right? Because we just found that out. We use molarity formula to get moles. We take the gram formula mass, use them in a proportion. 7 times 110, what's that, 70.7, right? They have 700, or I can't do math, I guess, 780 they have, right? 780 grams. Why am I going brain dead on that right now? 770. That makes way more sense. So 770, yeah. End of the day. Maybe I'm losing it a little bit here today. But yeah, 110 times 7, of course it's 770. Anyways, so that's the answer to number 4, and that's how you would do the 2-step molarity problem. All right, so that's it for the homework. You can put that away, take out your notes. That sounds weird, no one's here. But anyways, take out your notes. And I'm going to replay that part of the video. So you'll be watching a video on a video, just because it's easier than setting this all up during the video here when I'm not here. Anyways, I'm going to play the video for colligative properties, just to get the little the phrases kind of going in your head. And then we'll take some notes on colligative properties, and then that's going to be it. So if I stop a little short, you guys can use the rest of the class to do review book homework. Hopefully you can go get it if you have it in your locker or something, but we'll see. Sometimes I talk too much. So let me get the video going here. All right, here we go.
Salt the southern water in a beaker today. The ice broke apart in the usual way. They made it harder for the water to boil and freeze, so the freezing temperature changed a few degrees. Colligative properties, concentration. Colligative properties, concentration.
So that's the thing I want you to remember. Colligative properties depends on concentration. And yeah, they spelled it wrong. What is concentration? Is basically how many particles are dissolved in a certain amount of solvent. So the more particles, the higher the concentration, the more these colligative properties are affected. And I'm going to teach you what that is, or what they are. The video talks about boiling point and freezing point. So you do need to know about the boiling point and freezing point and how this changes that. So here we go again.
Electrolytes have a greater effect on the melting and boiling point of the solution than non-electrolytes.
So all they're saying there is that electrolytes have a bigger effect on the colligative properties. So I'll explain that after the video.
More solutes the salt got more effect. Solution's boiling point increases direct. The freezing point decreases, which is really nice. In the winter, salt the road to prevent the ice. Add a solute, boiling point goes up. Add a solute, freezing point goes down.
One more time, hold on.
Ice. Add a solute, boiling point goes up.
So that's something I need you to remember. Add a solute, boiling point goes up. So a solution always has a higher boiling point than just the pure solvent. What does that mean? Salt water maybe boils at 105, but pure water boils at 100. So the salt makes the boiling point go up. That's colligative properties.
Add a solute, freezing point goes down.
So freezing point goes down, boiling point goes up, freezing point goes down. So they stretch out the scale. Freezing point goes down, meaning salt water might freeze at -10. That's why when you put salt on the roads in the winter, it has to be colder for it to freeze, right? It melts the snow, reason for that is it can no longer be frozen if there's salt involved because it drops the freezing point, so it melts. So whatever temperature that snow or ice is at, it's above the freezing point, so it's going to melt. That's because salt is added. So salt water affects the freezing point. It brings it down. But pure water pure water freezes at 0, so that's different, right? 0 would be up here somewhere. So water has a higher freezing point. Salt water, for example, would have a lower freezing point. So again, that's colligative properties. All right. Let me go get the lights quick. All right, here we go. Colligative properties. All right. These are physical properties that depend only, I'm going to capitalize that, underline it 3 times, only depend on, oh, wait, I wrote the pen. Physical properties that depend only on the number of dissolved particles and not the nature of the particles. I'm going to give you a minute to get that down. So what this means is these properties are only affected because of the number of dissolved particles. It has nothing to do with what the particle is. In other words, salt, sugar, potassium nitrate, copper sulfate, iron chloride, whatever. The nature meaning like the chemical bonds, like ionic, covalent, polar, nonpolar, whatever. As long as it dissolves and it produces particles that are dissolved in the solution, that's what affects the properties. It has nothing to do with whether it's an Na plus or an I minus or a Ca plus 2 or whatever. It doesn't matter really what it is, it's just how many particles there are. And the key here is the more dissolved particles equals a larger, or has a larger effect. In other words, the boiling point, freezing point, and there's one more, vapor pressure, I'll write it down. Those 3 things, vapor pressure, boiling point, freezing point, are more greatly affected the more dissolved particles there are. So if you have a beaker of water and you put one little pinch of salt in it, it's hardly going to affect anything. But if you dump, a few teaspoons or tablespoons of salt in that beaker, that's going to have a bigger effect because you're adding more dissolved particles, more salt. So that's what that means. So more particles mean larger effect. So let me write down boiling point, freezing point, and vapor pressure, and then we will get into the details. All right. So the 3 colligative properties, it's called boiling point elevation, and that's because a solution has a higher boiling point than a pure solvent. So salt water is the solution, right? And then water is just the solvent. So water boils at 0, salt water boils at 100. I mean, scratch that. Sorry, losing it here. Water boils, well, let's write it down. H2O boils at 100 degrees Celsius, but NaClAq, salt water, let's say, boils at 110. So boiling point elevation means the boiling point goes up, AQ, right? It's a solution. When you dissolve that salt, it increases that boiling point. So that's the first one. It's called boiling point elevation. I'll give you a minute to write that down. I'll explain why this happens once I'm done with the freezing point and vapor pressure. So I'll give you notes on the freezing point, notes on the vapor pressure, then I'll explain why these things happen, and then I'll probably stop there. So probably pushing 15 minutes right now. Should be good. All right. So that's that. Freezing point depression. Freezing point depression. All right, so freezing point depression means the freezing point goes down. So what does that mean? A solution has a lower freezing point than a pure solvent. So again, H2O freezes at 0 degrees, but NaClAq maybe freezes at -10 degrees. So the freezing point of the solution is lower than the freezing point of the pure solvent. So again, the colligative properties depends on concentration. That part I haven't really addressed yet of that video. The jingle, we'll call it. The other part though, add a solute, boiling point goes up. That was the first one. Boiling point. Add a solute, freezing point goes down. That's this one. So it helps to like say that over and over. I know it's kind of cheesy or whatever, but whatever works, right? So add a solute, boiling point goes up. Add a solute, freezing point goes down. And again, I'll explain in a little bit why. But those are two colligative properties. So we got boiling point elevation, freezing point depression. Hopefully you've had time to write that down. Next is vapor pressure. It's called vapor pressure lowering. It's not called vapor pressure depression. I guess that kind of sounds weird. But vapor pressure lowering. I have trouble saying that. That sounds weird to me. Vapor pressure lowering. Anyways, it's exactly what it sounds like. So a solution has a lower vapor pressure than a pure solvent. And I don't have a good number. I guess I'll just make something up. H2O at room temperature, 25 Celsius. Oh, I don't even know. I don't have a concept. Let's just say water is 50 kPa. That's a pressure. I don't think that's right, but for the sake of the notes here, we'll say water is 50. Salt water, AQ, let's say is, like 30 kPa. So in other words, when water is by itself, it evaporates and that vapor collides and creates pressure. It's called vapor pressure. So any water, sitting in a glass or a beaker, water is giving off vapor and they're colliding with each other, maybe with you if you're close enough or whatever. That's vapor pressure, right? Vapor particles colliding. Salt water, there's actually less vapor coming off. Less vapor produced, therefore less vapor pressure. So in a minute, I'm going to explain why vapor pressure goes down, why boiling point goes up, why freezing point goes down. This is the best one to kind of use to explain why. So I will talk about this one first, but it applies to boiling and freezing as well. So a solution has a lower vapor pressure than a pure solvent. Okay, should be good. All right, so why? Why do these things happen? Why does the boiling point go up? Why does the freezing point go down? Why does the vapor pressure go down? So the question is, why? Here's why. When you dissolve a, we'll just say solute in, we'll say water. We'll just use water as an example. In water, you are increasing, and this is where I kind of wish I was here for real to ask the question and get you thinking about it, but I'm going to have to tell you here because you're not here. But when you dissolve a solute in H2O, you are increasing this. Now what is this? Well, water by itself has this, or else the water would just completely break apart. If water didn't have a fairly strong this, it wouldn't hold together in a liquid phase, it would just be a gas all the time. So hopefully some of you are thinking, what is this thing that holds water together? Well, water has this. If you add solute to water, you're adding more interactions in the water, therefore increasing this, and hopefully this you're thinking of is forces of attraction. When you dissolve a solute in water, you are increasing the forces of attraction. So I think of this kind of like when you put salt in water, the salt dissociates, breaks apart, Na plus Cl minus, like in the video and like the worksheet from last week. The water is attracted to the Na plus, the water is attracted to the Cl minus, and as a result, you're making that solution stronger because you have more of these interactions going on. I'll draw a picture, but I think of it, I didn't explain myself there, I think of it kind of like the salt particles are like little anchors. So they're like holding the water down in the beaker and it can't evaporate, so therefore it can't boil and it can't have high vapor pressure. Freezing point's a little trickier, but same concept. So let me draw an example here. I'll draw some pictures. So if you have just pure H2O, and then you have NaClAQ, think of it this way, you have a bunch of, we'll just draw a couple. We have H2O, draw a couple of H2Os in there, dotted line between them, right? Might be hard to see. There's a dotted line there, that's hydrogen bonding, right? So we can draw another one maybe, another water molecule. So you have hydrogen bonding, but you only have one force. So you have H bonds. So that's just one type of force in there. Over here, you have Na pluses and Cl minuses, and if you remember, the oxygen, right, so I'm going to draw the water backwards, O, H, right, H2O. The O is attracted to the Na, so there's a dotted line there, and then the H2O over here, I'll draw the water again backwards, the H's are attracted to the Cl, and I didn't draw it big enough, but we've seen it over and over again. The water surrounds the ions. So not only do you have water attracted to water, but you also have water attracted to the ions. So you have two forces of attraction. So you have one, you have H bonds, that's forming between the water, just like that. And then on top of that, you have a force that you may or may not remember off the top of your head, but this is called molecule ion. Your molecule is water, ion are the ions, Na plus Cl minus, so you have molecule ion attraction. So you have two types of attractive forces and just one here. Therefore, over here, water can evaporate fairly easy, relatively speaking. What does that mean comparing to this? Where over here, you might have just a little bit. So water has a hard time getting free, breaking free, because it's being held down, being attracted to these Na plus Cl minus. So if you try and boil this or boil this one will boil first, right? That's when the vapor will start to come off, very rapidly. So this will boil first, lower temp, because there's less forces to break. because when you boil, that's what you're doing. You're breaking those forces, not bonds, forces. Same thing here. When you boil salt water, everybody here knows salt's left behind. Water goes away. So you're essentially breaking these forces when it boils. So if you have two forces you got to break versus one, and you're giving them both the same amount of heat, let's say, or not even, it doesn't even have to be the same amount, but just to be fair, give it the same amount of heat. This one's going to take longer, and it's going to boil at a higher temperature because it needs more energy to break those forces. It needs more energy to break those forces. That's why the boiling point goes up. That's why the vapor pressure is less. There's less vapor being produced. More vapor here, higher vapor pressure. And then freezing point, the reason this salt water would freeze slower and at a lower temp is because it's hard to draw. I really can't. I'm just trying to explain. When ice forms crystals, so they form like, geometric patterns, kind of like snowflakes, they form those crystal shapes. When they form those crystals, the water, the salt, the Na plus Cl minus, because they're in there and they have this molecule ion attraction, it screws up that crystal formation. So it has to lose even more energy to freeze because it has the extra force. You don't really need to explain that on a test or anything, but I do expect you to have some idea and understanding, and hopefully you're following me, that if you have more forces, it's harder for the water to get out. So vapor pressure should make sense to you, and boiling point should make sense, that it just can't evaporate as easily because there's more forces holding it down. So that's the explanation for why the colligative properties exist. Why freezing point goes down, why boiling point goes up, why vapor pressure goes down, and hopefully that helps a little bit. The depends on concentration part of the video, I'll wait and teach you guys Friday, or tomorrow, I guess, for you guys, because it's probably at least 20 minutes here, so that's probably good enough. But that's colligative properties. You will have a worksheet, probably due Monday. I'll give it to you Friday. I know you don't want to hear that, but we gotta do what we gotta do. So whatever time's left in class, I would work on that review book assignment. So if you need to go get it, as long as whoever's here with you guys doesn't mind you going to get it, go get your review books and get working on that. So that's it. So hopefully this was pretty helpful, not super boring, and trying to think if there's anything I'm forgetting. I guess that's it. All right, so I will see you guys later.